welcome to this webinar. My name is James Hernandez, and I am with the Engineering Services team here at Zemax. And today we're going to be looking at how to use OpticStudio. On this webinar, we're going to be using OpticStudio 16 to model omnidirectional sensors that may be used on autonomous vehicles. Now, this webinar is really going to be geared towards individuals or companies who are interested in potentially pursuing designs of autonomous vehicles and want to design optical sensors for their systems, but may not be too familiar with OpticStudio or just have a general idea of optical design itself. So hopefully we're going to be able to provide you with some useful tips and tricks that'll help you out in these designs. So as a bit of a background, optical sensors are currently a huge topic of interest when it comes to autonomous vehicles. We have obviously UAVs and drones that are being used for a variety of applications, not just defense applications, also in commercial and recreational applications. Autonomous vehicles, and that's obviously a big one, trying to eliminate the human error factor that goes into the driving experience. Automated guided vehicles, those are more seen in factory settings to transport materials across the plant. And obviously military robots that can be used for attack, search and destroy, and a lot of other things. And here are just some real world examples. Like I said, we have drones, AGVs, here in that second picture, obviously, like I said, transporting raw materials from point A to point B on the factory floor. Military vehicles, as in the Talon project from Foster Miller. And perhaps the most popular example of the self-driving car, the Google concept there to the right. So the optical sensors that are used on these systems can be modeled pretty easily on OpticStudio. And the software provides a lot of system performance and analysis features that will make excellent tools in designing well-functioning system. And here we're going to be presenting just one example, and we're going to be showing the analyses that designers might find useful when designing their own. So just starting out with an objective, we're going to say that our objective is to design an optical sensor that may be adapted for use on an automated guided vehicle or a compact military robot. There's going to be a wide variety of ways that we can achieve this. We can use a rotating camera design, essentially just having a fixed, non-wide angle camera that we're going to mechanically rotate. We can use a fisheye lens to get that wide field of view. We can use a catadioptric lens system, which is just a combination of mirrors and lenses in one system, or any combination of the above. So there's a wide variety of ways that one can approach this problem. So as the marketing requirement, again, this is all just hypothetical, but let's just say to keep costs low, manufacturing pretty easy, which is a pretty universal goal. We're going to only use spherical surfaces in our design, and that includes mirrors as well, so no parabolic mirrors. The system length should be kept pretty small, below 65 millimeters preferably, and the lens diameter should be kept below 20 millimeters. The operating wavelength is going to be in the visible spectrum. Of course, there are some systems that may be more inclined to use the infrared spectrum, but here we're going to use the visible spectrum. And the key requirement is that we will provide a 360-degree field of view. On to our technical requirements. Out of the many ways that we said we could approach this problem, we're going to choose to model a catadioptric system, and that's again just a system that utilizes reflection and refraction via lenses and mirrors. Again, from our marketing requirement, our system length is not going to exceed 65 millimeters, and our lens diameters will not exceed 20 millimeters. And the operating wavelength that we're going to choose in OpticStudio is going to be the FDC spectrum. Again, that's going to be 486 nanometers, 588 nanometers, and 656 nanometers to approximate that visible spectrum. The field of view, again, is going to be 360 degrees in that horizontal plane. Now, obviously, we also have to define a vertical field of view, and we're going to set that to be positive 53 degrees and negative 15 degrees from that horizontal reference plane, and we'll see why here in a bit. Our RMS spot size, we're going to keep that below 35 microns just to keep the spot small and motivate aberration balancing. So now moving on to why we chose those values for the vertical field of view. Those values are obviously going to be determined by the range and mounting position of that sensor, and that's going to be unique to every system. So here, let's just say hypothetically we're going to consider this scenario that our vehicle is going to be operating at full speed while approaching some obstacle, and once that obstacle is detected, we have to have enough time and space to brake in order to avoid collision. The velocity of our vehicle is going to be 2 meters per second. Maximum time for detection, tracking, and classification is going to be about 1 second. And our braking acceleration is going to be 1 meters per second squared. Now, that's going to be hard braking. It actually would be 0.5 meters per second squared if we were doing soft braking, quote unquote. So from this data, we see that a person running at 2 meters per second is safe so long as the detection range is equal to or exceeds 10 meters, assuming that we're actually using hard braking. So that's the minimum range that we'll need, and we'll round that up to 11 meters just to be safe. Again, the sensor might not be mounted directly in front of the vehicle, so just to be safe, we'll add 1 meter more. So at 11 meters, our object must be detected. Now, we're also going to assume that our camera is going to be mounted approximately 3 meters off the ground. So just to show you what we're working with, so that's just kind of a cartoon representation of what we just discussed. And that derivation shows that the field of view vertically downward has to be negative 15 degrees. What about vertically upward? Some applications might require some decent field of view in the opposite direction. That may not be the case for an AGV, but it might be crucial for, let's say, military robots that have to be aware of, what's going on in the sky. So we're going to specify positive 53 degrees derived in the same way that we just derived the negative 15 degree requirement, assuming that we want to detect an object 11 meters away at a height of 8 meters above the camera. On with the technical requirements, we're going to set an f number to be at or below f2.8. We want a fast lens here, so our system works pretty well under dimmer light conditions. And finally, we're going to specify our image sensor to be the Allied Vision Manta G419 CMOS camera. And that's just a sensor that's commercially available. And the importance of that is that the sensor is going to essentially specify what our MTF requirement is for our system. And that's going to be a minimum of 20% contrast at 90 line pairs per millimeter. And that's just going to be just above the Nyquist frequency of the sensor, which will help us ensure that we avoid aliasing. And here are just the specifications on that sensor. Again, we're going to be using a progressive scan CMOS with a sensing area of 11.3 by 11.3 and a pixel density of 2048 by 2048. But again, the important specification here is that Nyquist frequency. So now that we've specified all of the requirements for our system, which for me is the most important part of the design process, we can now begin to actually see how we can model it. So to do so, we're going to take a bit of a breakdown approach. So first, we're going to look at the catoptric system, which again are the mirrors that will collect light from a wide field and redirect it so as to be imaged down. And then we'll look at the dioptric system, which is the series of lenses that will actually image that light down onto the sensor. Coupling both systems will be the slightly tricky part, but we'll see that it can be done here in a bit. This is a visual introduction as to what we'll be designing. We're going to be utilizing a 2-mirror configuration. Essentially, we're going to be utilizing a spherical mirror followed by a planar mirror. And that planar mirror may become slightly curved during the optimization process, but we'll save that for later. So physically, we're going to see the planar mirror followed by that spherical mirror. But in an optical sense, we're going to say that incident light is going to come on to that spherical mirror, be redirected towards the planar mirror, which will finally redirect the light into a central hole in that spherical mirror, which will be where the dioptric system takes over. So now to actually translate all of these ideas onto OpticStudio, we're going to say that we're going to set our entrance pupil diameter to 0.25 millimeters, and we'll check later that our F number requirement is fulfilled. Our fields will be set at 37, 60, 89, and 105 degrees. Now our system is symmetric, so there's no need for negative counterparts. And you might be asking, why are we setting our extreme fields to be 37 and 105 degrees when earlier we said 53 and negative 15 degrees? Well, that's true. But since earlier we assumed that our system was going to be vertically mounted, and here we're designing the system such that the mirrors are pointed along a horizontal optical axis, the geometry shows that 53 degrees and negative 15 degrees actually correspond to 37 and 105 if modeled horizontally. Now our wavelengths are going to be, again, FDC. And to determine what the radius of curvature of that spherical mirror and the distance between the two mirrors are, we can use the lens maker's equation and the approximation for the power of a spherical mirror to find a combination that works. Now, there's an infinite amount of possibilities, and we'll just choose one here, as we'll see here in a bit. And the last bit of information that we need to know is that we need to size the central hole in the spherical mirror so as to avoid vignetting. And we can just use the layout to really see that we're avoiding vignetting, which is important just for the efficiency of our system. Chosen configuration will say that the radius of curvature of that spherical mirror will be 21.5 millimeters with a central hole radius of 4 millimeters. The radius of curvature of that planar mirror is obviously infinity, and we'll set the mirrors to be at a distance of 18.5 millimeters apart. Now, trial and error is always an option in OpticStudio, so you can really play around with all of the infinite amount of configurations until you find something that works for your design. OpticStudio will scale the semi-diameters of these elements so as to pass all of the light rays, but rounding up to a more functional value is obviously recommended, as is adding a chip zone for mounting considerations. So going into OpticStudio, we can see that we've entered in all of our data as in that slide. Our aperture type, fields, wavelengths, and our LDE reflect that. We can see that we've added in a dummy surface to see that incident light coming in from infinity. Our material for those two surfaces have just been specified as mirror. Again, since we're not utilizing refractive surfaces here, we don't need to specify any type of glass type. But one thing that the user should note is that we've entered in the thickness as negative 18.5 millimeters instead of positive 18.5 millimeters. And again, just remember that since light is coming in incident onto that spherical mirror and not the planar mirror, it's going to have to travel backwards 18.5 millimeters, which is why we've added in that negative. So that's just something to note.
So now that we have that, we can move on to our dioptric system design. And the goal here is relatively simple. We just have to image down the light collected by our mirrors. But in doing so, we have to ensure that we correct for aberrations as much as possible before coupling this system in. That'll make aberration balancing of the coupled system a lot easier during that optimization stage. So just some strategies that we can consider, and this is just general knowledge that an experienced optical designer would know. We can utilize combination of opposite power, symmetry with respect to the stop, a field flattener if field curvature becomes a problem, and obviously some defocus to correct for the wide variety of aberrations. One thing that we should know before we begin is that the design is also in part dictated by the catoptric system, meaning that it must be designed so system coupling is even possible. And this is the important factor to consider, that the full field exiting ray bundle of the catoptric system needs to be matched to the full field entering ray bundle of the dioptric system. So essentially, just to provide some insight, every field point in a system may be defined as a ray bundle source, and the maximum radial extent of the ray bundle, off-axis or on-axis, may be defined as the height of the chief ray plus the height of the marginal ray. Now, the entrance pupil and exit pupil of the system define the cones of light entering the system, and the angle of any ray bundle may be defined by the angle of that chief ray. To ensure that the full field exiting ray bundle of the catoptric system equals the full field entering ray bundle of the dioptric system, we just have to ensure that the exit pupil diameter of the catoptric system equals the entrance pupil diameter of the dioptric system. And we have to ensure that the angle of the full field chief ray equals to the half field of view of the dioptric system. So again, this is just kind of what we're discussing. If we have our mirror system here and this is our full field ray bundle, that has to be matched to the full field entering ray bundle of our dioptric system. So to determine the angle of that chief ray for our full field, a real ray trace would have to be performed. If performed manually, that's a tedious and tiresome process. But using OpticStudio, it's pretty easy. So here we can just use the RAID operand in our merit function editor to determine the real ray incident angle onto that stop surface of our mirror system. The incident angle will equal the exiting angle since the stop has no power, obviously. And in this case, that's 16.898 degrees. See what I'm talking about? We can go back into our Catoptric system file, open up our merit function editor, use that RAID command on surface 4, specify the full field, and we see that our angle of interest is 16.898 degrees. Now note that surface 4 is the surface of interest because it not only is our stop surface, but it would also be the location of our exit pupil, since there are no optical surfaces following the stop surface. So knowing that angle, we can also go into our lens prescription and find the exit pupil diameter, which again is important because that will need to be the size of the entrance pupil for our dioptric system. So to now summarize what we found, we'll say that our full field of view for our dioptric system will be set at 40 degrees, found by taking that approximately 17-degree angle found in the RAID operand, multiplying by 2 and rounding up for both functionality and some room for error. The Catoptric lens system prescription said that the exit pupil dimension was 5.015 millimeters, so we'll set the entrance pupil diameter of the dioptric system to be 8, again rounding up for functionality and error. And finally, to couple both systems, we'll simply overlay them such that the entrance pupil of the dioptric system physically overlays with the exit pupil of the catoptric system. And again, this is really simple. We'll just use the lens prescriptions in each file to check for the locations of the corresponding pupils, and then copy and paste the LDE of the dioptric system into the LDE of the catoptric system, and changing the thicknesses to ensure that the exit pupil and entrance pupil overlap.
So now going into OpticStudio, we can begin to analyze the result of implementing a dioptric system that fulfills the parameters we've just discussed in with the catoptric system and seeing what we're working with before optimizing. And the reason I've decided to skip ahead a bit and show you this result is because, as in the case of the catoptric system, the dioptric system really has many configurations that will work, even more so than the catoptric system. And the designer really has a lot of freedom to work with and still get the system to function properly. So if we go here into the Analyze tab and we look at our cross section, we can see that we haven't really chosen anything too complicated. Essentially, we have a series of 5 lenses, most notably just an achromatic doublet here, but everything's pretty simple, right? We have a combination of opposite powers to kind of help with that aberration balancing, but nothing too complicated. So again, we made sure that we've adjusted the thickness after that second mirror to ensure that our systems are coupled properly, and we can see that things are looking pretty good. So now that we can begin to analyze the system, we'll start out by looking at our spot diagram, and again we'll just go to the Analyze tab, Rays and Spots, and look at that standard spot diagram. And we can see that the results are already really encouraging even before optimization. Our RMS spot radius for all fields is well within spec, and that should remain consistent after optimization. Kind of building on that, we look at the aberrations going down here and open up our Seidel coefficients table. We can see that, as expected, from that spot diagram, our aberrations are pretty encouraging. We don't have too much spherical coma, and astigmatism are pretty well controlled. Before completing this preliminary analysis and moving on to the optimization stage, we'll just quickly take a look at the MTF plot for this system. And if we zoom in here a little bit closer, we can see that while everything else was encouraging, we're not yet meeting the MTF requirement of 20% contrast at 90 line pairs per millimeter that we set earlier. As you can see, the sagittal component of these fields are not meeting that requirement. So after that optimization stage, we'll definitely have to take a look and see if we've improved upon that. Before showing the results of the system optimization, I'll go ahead and lay out the general strategy that I use to optimize my system. And the viewer should be aware that there isn't anything too special about this strategy. This really pertains to optimizing all systems in OpticStudio. We'll go ahead and begin by optimizing for RMS spot size using the default merit function and starting out with 3 rings, 6 arms for that pupil integration. We'll then proceed to optimize for RMS wavefront using that default merit function and starting with the 3 rings, 6 arms with the pupil integration. But after that, it becomes a bit of an iterative process in that we'll be jumping back and forth between optimizing for RMS spot size and optimizing for RMS wavefront until the results are encouraging or at least close to what we want in terms of that MTF performance. The viewer should also note that as RMS wavefront error goes to 0, the MTF approaches that diffraction limit. So it really is important to focus on optimizing for the RMS wavefront before switching on to explicit MTF optimization operands. And we have a knowledge base article on that, optimizing for MTF, that really provides a little bit more information on why that is. If we go ahead and look at the results of that system optimization, just by looking at the lens data editor, there isn't anything that's too apparently different. We can see that we have added a slight curvature to that planar surface, planar mirror surface that is, following that optimization. If we go into the analyze, look at that cross-sectional view, again, I have added a bit of thickness to these mirror surfaces just by going into the surface properties and draw option. But other than that, everything's remained pretty consistent. Again, you can see that slight curvature that I mentioned earlier. Opening up the standard spot diagram, we will see that our spot sizes have increased a bit, but again, when we open up that MTF plot, we will see that that trade-off is one that we will be willing to take, especially since these spot sizes are well within the 35 micron limit that we imposed at the beginning. Just taking a look at the aberration content, again, we can see that aberrations have increased a bit, but again, everything is still well balanced. And again, that distortion is something that is expected with wide-angle systems. And now finally, looking at that MTF performance, if we zoom in, everything's looking a lot better, and all fields are well above that 20% contrast at 99 pairs per millimeter requirement. So with that being said, our MTF requirement has been fulfilled. As we just saw, our spot diagram falls within spec. We can see here that our system length and going into the lens data editor, our lens diameters all fall within spec as well. And finally, that working F number of 2.88 is close to the 2.8 limit that we imposed earlier. And again, we can fiddle with this design if we wanted to get it at or below 2.8. But overall, this design does seem satisfactory, and we can move on to the tolerancing of the system if we wish. So before we conclude this webinar, we'll just take a quick second to talk about the image analysis features in OpticStudio. OpticStudio features many useful extended scene analysis features, particularly the geometric image analysis, which may be used to model extended sources, analyze useful resolution, represent the appearance of image objects, and provide intuition as to image rotation. Now, the viewer should note that it will only trace rays and see where they land on the image plane. There's no fast Fourier transform and convolutions involved in that computation. So that computation time is definitely tolerable. We can go ahead and open up the geometric image analysis feature on our optimized file. And you can see here that we've just utilized the default inputs. Here we're going to try to trace a standard letter F. There's a variety of options that we can try to trace, such as a circle, grid, etc. And you can see here that the image analysis is showing that distortion that we expected. It does also illustrate our efficiency, which would be the total number of rays that reach that detector over the total number of rays launched. Here we're looking at the 37-degree field position, and it also provides us with the total power. So this feature is definitely useful if one wants to see what an image might look like if we try to trace it through our system. With that, we'll go ahead and conclude this webinar. I hope that I provided you with some useful tips and tricks to designing your own system. Please refer to the sample files that have been included with this webinar, as well as the knowledge base article, How to Design an Omnidirectional Catadioptric Sensor, for more information on the topics that we discussed today. Good luck with your own designs, and until next time, cheers.